Okay, so in this section, we're talking about continuity. And remember, a function is continuous if it can be sketched in one continuous motion without having to take off your pencil from the paper. So here is an example of a continuous function. And we're going to actually talk more specifically about continuity at a certain point. So if we have a function like f of x, right, our function doesn't have to be, it doesn't have to exist from negative to positive infinity. It could just be a curve that looks like this, something that starts at A and goes to B. Now, we can talk about continuity at a point, but there are essentially like two types of points we can talk about. So one is the point that we're talking about could be, here. So somewhere on the interior of the domain, right? And in that case, we say a function is continuous if the limit of f of x as x approaches c is the same as f of c. So just like in this case, the limit is this y value here, and f of c is that same y value. So that's the interior. So for that, for the limit, we looked at the left-hand limit and the right-hand limit. But what if we're talking about an end point? So for example, what if we're talking about point A here? In that case, you still have to make sure that the limit is equal to f of A, but I can't do a two-sided limit in that case. I can only do a one-sided limit. So what I have to say is check to see that the limit from the right-hand side only equals to f of A. And then if we're talking about point B here, then make sure that the left-hand limit is equal to f of B. All right, so that's an endpoint. And just to recall, the different types of discontinuities are removable is the first type where, like you see here, there is a hole here, but clearly there is an f of 0 there. So in this case, this is a removable discontinuity. And the way we describe it is we say the limit of f of x as x approaches 0 from the negative side equals the limit of f of x as x approaches 0 from the positive side. But this does not equal f of 0. So that's how you can prove that it's not continuous and that it's a removable discontinuity. A jump discontinuity can be described as if the limit of f of x as x approaches 0 from the minus side is not even equal to the limit of f of x as x approaches 0 from the positive side. So at x equals 0, there are different values from the left and from the right. Next, I have an infinite discontinuity. An infinite discontinuity happens when we have a vertical asymptote, right? And the situation where we have a vertical asymptote is when the limit of f of x as x approaches a value is infinity. So in this case, the limit as x approaches 0 from the negative side is positive infinity. And that's the same as the limit of f of x as x approaches 0 from the positive side, and those are both infinity or dne. And then the next type is an oscillating discontinuity. Okay, so to find the intervals of continuity and the points of discontinuity, what we do is you basically look at the function and you try to see where you have problem points, where you have points of discontinuity. So this one, when I factor this, it's x plus 1, x minus 2, x minus 1, and all this is a review, so we're just brushing through these things. You see that nothing from the denominator cancels, so we have infinite discontinuities at x equals 1 and x equals 2. That means this is continuous on negative infinity to 1, 1 to 2, 2 to infinity. Okay, for this next one, that's an absolute value function, and you're just expected to know how that looks and where the vertex is. In this case, it's here. That is a continuous function. For ln, again, all of these on this page are stuff that you should know without a calculator, right? You should know where discontinuities exist. You should know how ln looks. ln is the inverse of e to the x. That means instead of a horizontal asymptote, it's got a vertical asymptote. X minus 1 means everything is shifted to the right 1 unit. So the vertical asymptote is at 1 instead of it being at 0, and that just looks like that. So the condition for an ln is that the interior, the argument, x minus 1, has to be greater than 0, so x has to be greater than 1. That means that's the domain. All right? Now, along its domain, starting at 1, going to positive infinity, there are no discontinuities, so this is continuous from 1 to infinity. This one here was on the assignment for the summer as well. E to the x is totally fine, but this has 2 over x in the exponent. Well, that 2 over x, right, means that x can't be 0. That means there is a discontinuity at x equals 0. Now, because x happens to be in the denominator, right, it doesn't matter that the whole thing is in an exponent. Because x is in a denominator, it's an infinite discontinuity at x approaches 0. Okay. So this is continuous on negative infinity to 0 and here. Okay. All right. So we're going to skip over example 2 and 3 because the same exact ones are in the summer packet. But if we go to here to how a continuous function is defined, something is continuous on an interval if it's continuous at every point on the interval. So now the string of words continuous function means a function which is continuous everywhere on its domain. All right, so take a look at this graph here. This is the graph of y equals 1 over x, and you can clearly see there is an asymptote here, right? So x cannot be 0, which means the domain here is negative infinity to 0, 0 to infinity. Now, at x equals 0, this thing does not exist. So there is clearly a discontinuity there. But is this a continuous function? All right, let's check. So what's the domain of this? Negative infinity to 0, that's that. And it's continuous from negative infinity to 0. And then also 0 to infinity. So wherever it shows up on its own domain, it's continuous, meaning this is a continuous function. Okay? Now, can it be possible that something is not continuous on its domain? Yes, right? So take a look at this example here. The domain for this is all real numbers. It exists everywhere. But is this a continuous function? No, because there is a point within its domain where this function is not continuous. So this is not a continuous function. Okay, moving along. Composite functions. If a function is a composite function, if it's made up of 2 functions which are continuous, then the composite function is also continuous. So take a look at f of x here. It's built from two different functions, right? So let's see. So what is this built from? The outer function here is sine of x. The inner function is x squared plus 1. Now, because the outer function sine of x is continuous, and the outer function is continuous, and the inner function is also continuous, that means, therefore, that f of x, which is g of h of x, is also continuous. Right? So you have to know that theorem, that if a function is composed of two continuous functions, then it's continuous. Okay, next, intermediate value theorem. This is super, super important. It's got a nickname called the IVT, intermediate value theorem. Okay, what the intermediate value theorem says, if a function f of x that is continuous on the closed interval a to b takes on every value from f of a to f of b, meaning if a function starts at x equals a and ends at x equals b, at x equals a, its y value is f of a. Suppose that's like 1. At x equals b, its y value is f of b. Suppose that's like 7. Well, the theorem says that if this function is continuous, then on its way from one endpoint to the other point, it's got to pass through every single y value between 1 and 7. All right? Okay. Here, let's find a value so that the function is continuous. Okay, continuous means left-hand side and right-hand side have to equal to each other, right? So what we want is the limit of f of x as x approaches 2 from the minus side to equal the limit of f of x as x approaches 2 from the positive side, and we want all that to equal f of 2. Okay, so the limit of f of x as x approaches 2 from the minus side is, you plug 2 into the top function, you get 7. And then from the positive side, it's 2a plus 1. Now you want these to be equal to each other, so you say 2a plus 1 equals 7, so a is equal to 3. All right, so that's section 3. Now section 4 is definitely a review from last year, and everybody did well on the test, so we're not going to go into too much detail here. Just know how much work to show here. So for this one, you would do f of 4 minus f of 0 is equal to 3 minus 1 over 4, which is 1/2. All right. Same for b. We know how to do this one already. All right. In here, we have a little bit of a different situation, but it's exactly what we've been doing all along. This is the growth of a fruit fly population in a controlled experiment, and we want the average change. All right, so at one point we have P and then we have Q. So we want the average rate of change, that's, f of 2 minus f of 1 and so on. So we want delta P, the change in P, that's 340 minus 150 over delta Q, 45 minus 23, and that's roughly 8.636, but we need to have proper units. So what we have here in the numerator is the change in P, that's the dependent variable P, which is the number of flies, divided by delta T, which is the change in the independent variable time, given in days. So this is that many flies per day, right? And so what we found here is the average rate of change, which brings us to the next point, which says the slope of the secant line. And what we need to do here is recognize that the slope of the secant line is exactly the same as the average rate of change. All right? Okay, and so remember how we went from the slope of the secant line to the slope of the tangent line. The slope of the secant line had the formula of this, okay? But to make this into a tangent line, we moved our second point towards the first point, making the distance between them 0. So we brought h to be extremely small, like 0. And that became the slope of the tangent line. And again, something that we've done over and over since last year. So again, the exact same thing here is in your summer assignment. And people actually did rather well on the test with this. So I'm moving on. What I did want to focus on is example number 5, where at what point is the tangent to f of x horizontal? The tangent is horizontal means m is equal to 0. So first I have to find m, and m is the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, and I know how, I know that everybody knows how to work with this formula. So we work, and then several steps later, we get that m is equal to -4 minus 2x. So now we want m to be horizontal. So we take our we want m to be 0 and set it equal to 0. So -4 minus 2x will equal 0. X is equal to -2. But we were asked, at what point is the tangent horizontal? Point is x comma y, x and y coordinate. So you plug this into f of x, and we get that the point is -2, 7. Okay, moving along, normal. A normal line is actually the perpendicular to the tangent at some point, right? So any line perpendicular to a tangent is called a normal line. So here we have f of x equal to 4 minus x squared. So if that's 1, 2, 3, 4, that's how that looks. We want to find an equation for the normal to this. So at x equals 1, my point is right there. All right, so let's see how this is going to look. That's the tangent line. The normal line is perpendicular to the tangent line. That's how that looks. So what I want is to find the equation of that. And what we're going to do is we're going to find the slope of the tangent line, just like we always did. And then from that, find the equation of the perpendicular line, like in Algebra 2. So first, the slope of the tangent line is, again, same thing, f of x plus h, the limit, minus f of x all over h, dot, dot, dot. At the end of the day, you get that the slope is -2x. So at x equals 1, m is equal to -2. This is the slope of the tangent line. Now, the normal slope is the negative reciprocal, so positive 1/2. And so now I'm ready to write my equation for the normal line here. Okay, so if my x is equal to 1, f of x, or f of 1 rather, is 4 minus 1, 3. So all this is happening at 1, 3. So my line is y minus 3 is equal to 1/2 x minus 1. That's the equation of the normal line. That's the equation of that red line over there. Last but not least, we have speed. And again, this was on the last test even, and I think everybody did well on that one. So I'm not really going through it in detail, just reminding you that again here we need to apply the same formula. Okay, all right, and that is sections 3 and 4. Thank you, and I will see you in class.